Welcome to the Deep Dive. We sift through stacks of research and articles to bring you the core insights. And today, wow, we're diving into something really fundamental in physics, the hunt for a theory of everything, a TOE.
The ultimate prize, you could say.
Exactly.
Okay.
But here's the twist. A recent paper, and Lawrence Krauss is one of the authors, makes this pretty bold claim. It suggests that mathematically, a final theory of everything might actually be impossible.
Impossible. That definitely goes against the grain for a lot of theoretical physics.
Right. So that's our mission for this deep dive. Figure out what a TOE is supposed to be, look at the three big mathematical arguments this paper uses to say no way, and then talk about what that really means.
Yeah, it forces us to ask some pretty deep questions about what we can actually know, doesn't it? Especially in physics.
It really does. So let's start there. What is a theory of everything? People throw the term around, but what does it mean to a physicist?
Okay, so basically a TOE is meant to be this single unified theory. The idea is it explains all known physical phenomena. Everything.
All. Like not just gravity over here and particles over there.
Exactly. It needs to bring it all together. So that means combining the standard model of particle physics that's, quarks, electrons, the forces like electromagnetism.
Stuff.
Right. Combining that with Einstein's general relativity, which is our theory of gravity. And crucially, it also needs to explain the big mysteries we still have.
Like dark matter and dark energy.
Precisely. Those are huge gaps in our current picture. A TOE would ideally account for those too. It's meant to be the final word.
The final word. Stephen Weinberg called it the final theory, didn't he?
Yeah.
Like the point where there's nothing left to explain.
That's the dream, yeah. A point of complete understanding.
Okay, grand dream. So why the pushback now? Why this claim of impossibility? Let's get into the first big challenge they raise, which comes from math. Gödel's first incompleteness theorem.
Gödel. Right. So Gödel's theorem, put simply, it says that for any formal mathematical system that's consistent, meaning it doesn't contradict itself, there will always be true statements within that system that the system itself cannot prove.
Okay, hold on. So a system can be perfectly logical, but still unable to prove certain truths that exist inside it.
Exactly. There are inherent limits. Now, if you think of a theory of everything as a potential formal system describing the universe,
then Gödel's theorem would apply, meaning even a perfect TOE couldn't prove everything about the universe it describes. It wouldn't be fully complete.
in that strict formal mathematical sense, yes, that's the argument. Even if your TOE is consistent, Gödel suggests there will be physical phenomena or truths it simply cannot derive or prove from its own axioms. It leaves gaps.
That sounds like a pretty fundamental crack in the foundation, doesn't it? How do physicists respond to that? Because they are still searching.
Well, this is where the paper brings in a really important counterpoint. Physicists, in practice, rarely set up their theories like fully rigorous, axiomatic mathematical systems.
They don't write down all the rules like Euclid did for geometry.
Not quite in that exhaustive way, no. They rely more on observational consistency. Does the theory match experiments? Does it make predictions we can test?
So it's more about empirical success than pure mathematical completeness.
Exactly. The argument is, for a physicist, a theory is good if it works, if it describes reality as we observe it. They're not necessarily aiming for that absolute logical completeness that Gödel talks about. So the question becomes, does a physical theory need to be Gödel complete to be considered a theory of everything? Maybe not.
That's a really interesting distinction. It's like the map doesn't have to prove the existence of the territory in some abstract way. It just needs to help you navigate it.
That's a good analogy, yeah.
Okay, so incompleteness might be a mathematical feature, but maybe not a practical roadblock for physics. But what about the next argument? This one sounds even stranger. The task indefinability theorem, defining truth.
Right. This one is maybe less famous than Gödel, but potentially just as tricky. The core idea here from the paper is that within a proposed final theory, you might run into problems defining what truth even means in a consistent, universal way within that theory.
How so? Like what's an example of that?
Well, the paper uses a classic example from quantum mechanics, the measurement problem. Does the wave function really collapse when you measure it?
The Schrodinger's cat situation. Is it alive or dead before we look?
Kind of, yeah. Different interpretations of quantum mechanics give different answers to what's really happening. The math works beautifully for predictions, but the underlying truth of the collapse, or non-collapse, well, the theory itself doesn't definitively settle it. It depends on the framework you choose around the math.
So the task indefinability theorem suggests that even a TOE might have these built-in ambiguities. where it can't actually define the truth of certain situations it describes.
That's the implication. If the theory itself struggles to pin down what true means for some of its own core concepts, can it really be a theory of everything? It might leave fundamental questions about reality unanswered, not because it's incomplete, but because truth itself becomes slippery at that level.
Okay, that's mind-bending. But again, how does the practical physicist view come back in here? Is it another case of, if it predicts things, who cares about the philosophical definition?
Pretty much. The physicist's stance, as presented in the source, leans heavily on empirical truth. What can we measure? What can we observe?
If the theory predicts the outcome of the experiment correctly, that's the truth that matters for physics.
Largely, yes. If the model matches reality in all measurable ways, its usefulness is established, even if there are, let's say, philosophical loose ends about underlying reality or definitional purity. It's about building predictive models that work.
Right. Practicality trumps philosophical neatness again. Okay, that brings us to the third argument, which seems to be about sheer complexity. Chaitin's algorithmic complexity, what's that about?
This one comes from computer science, actually, from algorithmic information theory. The basic idea is about complexity, specifically the complexity of information.
Okay.
Think about a random string of numbers, like just pure noise. Chaitin showed that some strings are so random, so complex, that the shortest way to describe them is just the string itself. You can't compress it into a simpler formula or program. It's algorithmically irreducible.
There's no pattern to exploit, basically.
Exactly. It has maximal complexity.
Yeah.
The argument then applies this to physics. What if some parts of the universe or some phenomena are similarly complex?
What kind of phenomena?
The paper suggests maybe the chaotic dynamics inside a black hole, or perhaps quantum fluctuations at the Planck scale, the very smallest level of reality. What if these systems generate information or complexity that's fundamentally irreducible?
Okay, and if they do, what does that mean for a theory of everything?
It means that a TOE, which would presumably be a finite set of rules or equations, might simply not have the descriptive capacity to handle that level of complexity. It hits an informational limit.
So the theory just breaks down. It can't compute or explain what's happening in those super complex regions.
Potentially, yes. It might be informationally insufficient. Like trying to describe an infinitely complex fractal with a finite sentence. You just can't capture it all.
That sounds like a serious limitation. A theory of almost everything, maybe.
Well, again, there's the practical pushback. And it's similar to the others. Real-world physics deals with measurements. And measurements are always finite. They have limited precision.
So even if, theoretically, the complexity inside a black hole is infinite or irreducible.
What we can ever measure about it from the outside, or even theoretically probe, might still be within the complexity limits of our theory. As long as the theory's complexity threshold is higher than anything we can actually observe or interact with, it's still useful. It's still, for all practical purposes, a working theory.
Okay, so it feels like a recurring theme here. These mathematical arguments point to potential, absolute limits based on logic and information theory.
Right, limits on what a purely formal system can achieve.
But physics, as practiced, is maybe more pragmatic. It's about building the best possible models of what we can see and measure, even if those models aren't perfect in some abstract mathematical sense.
That's a great way to put it. These arguments aren't necessarily saying physics is doomed or that we should stop trying. It's more about adjusting our expectations of what a final theory might look like.
Less about mathematical perfection, more about empirical power.
Exactly. It highlights that physics operates at this interface between rigorous mathematical structure and messy observable reality. You need the rigor, but you also need the connection to experiment. It's a balancing act.
So the fact that a theory might not be able to prove all truth or define truth perfectly or describe infinite complexity, that doesn't make it useless.
Not at all from this perspective. A theory can be incredibly powerful, predictive, and unifying, even with those formal limitations. The source actually includes a great quote that gets at this spirit, something like, "To me, science is more than a profession. It's a way to understand the world and how to solve problems."
That puts it nicely. It's about the process of understanding and solving, not necessarily reaching some mythical absolute endpoint.
Right. The journey, the discovery, the problem solving, that's the core of it.
So when we take a step back from this deep dive, looking at this paper and its arguments, It really feels like an invitation to think differently about understanding the universe.
Yeah, it challenges that assumption that everything should neatly compress down into one single, logically perfect framework. Maybe the universe is just messier than that in some fundamental ways.
It highlights these mathematical, logical, maybe even philosophical speed bumps on the road to a theory of everything.
And recognizing those limits is important. But here's the paradox, right? Even if that perfect, mathematically complete toe is technically out of reach.
The search for it is still incredibly valuable.
Absolutely. Pushing towards that goal, even if unattainable, forces us to refine our theories, make new discoveries, and understand the universe better and better. The pursuit itself drives progress.
And for you listening, this whole discussion really challenges us to think about knowledge itself, doesn't it? What does it mean to know something completely? What are the limits of information?
It makes you question those assumptions about certainty and completeness.
Definitely. So here's something to chew on after we wrap up. What does it truly mean for our understanding if the universe, no matter how well we model it observationally, always contains some frontier beyond what our formal theories can fully grasp or prove?
A deep question indeed.
If you want to explore some of these ideas further, the source material suggests looking into Gödel's incompleteness theorems, just to get the background.
And for the physics side, especially quantum mechanics concepts like wave functions, superposition, entanglement, maybe check out resources like brilliant.org. They often have good explainers.
Okay, that's our deep dive for today. Hopefully it gave you some new perspectives on the ultimate quest in physics and the fascinating limits of knowledge itself. Thanks for joining us.